For decades, the standard cosmological model assumed the force pushing our galaxies apart was a constant. But recently, a massive map compiled by the Dark Energy Spectroscopic Instrument, or DESI, indicated that as space stretches and warps, dark energy might actually be changing. Just months later, another massive international cosmology experiment released its final results. The Dark Energy Survey, or DES, aimed its telescopes at a massive swath of the southern sky to gather its own set of answers. But neither of these billion-dollar, decade-long experiments actually measured dark energy directly. The cosmic signals we receive, faint flashes of exploding stars, tiny shape distortions in distant galaxies, are incredibly subtle and hopelessly tangled together. There is no isolated, direct signature for dark energy that a telescope can simply capture. So modern cosmologists don't actually search for our exact universe in the data. Instead, they mathematically define every possible hypothetical reality, and they ruthlessly eliminate the ones we clearly don't live in. This 3D grid represents what physicists call parameter space. It is a theoretical arena containing infinite hypothetical universes. Each glowing point is a distinct reality, dictated by slightly different ratios of cosmic ingredients: dark matter, regular matter, light, and dark energy. Decades ago, astronomers asked how cosmic expansion dimmed distant, exploding white dwarf stars. The data returned an answer sweeping across the grid, instantly proving vast swaths of realities impossible. Any universe lacking dark energy was eliminated. Every precise physical measurement we take acts as a cosmic filter, culling millions of counterfactual universes in an instant. The DESI project applied its own unique filter to the cosmos. It tracked baryon acoustic oscillations, which are essentially fossilized sound waves frozen into the distribution of galaxies since the infant universe. But relying on this one measurement leaves what statisticians call a degeneracy. Multiple, wildly different hypothetical universes could produce those exact same fossilized sound waves. This diagram shows how degeneracy works. If an experiment tells you that two unknown numbers add up to 10, the answer could be 5 and 5, 6 and 4, or 9 and 1. The data is accurate, but the exact reality remains ambiguous. To solve this, DES ran an entirely different physical test using the Blanco 4-meter telescope. Instead of sound waves, it mapped how invisible dark matter halos warp the light of distant galaxies through weak gravitational lensing. Now we overlay a new mathematical test onto the previous diagram. If the universe answers that those exact same two numbers must also multiply to 24, the incorrect options fall away. The remaining reality has to be 6 and 4. By combining entirely different observational data sets, the independent ambiguities cancel out. The experiments work together to slaughter the remaining incorrect realities. When cosmologists cross-examined the universe using the combined filters of both DES and DESI, the standard model held up. A universe dominated by a constant, unchanging dark energy survives the gauntlet. This zoomed-in data plot reveals two distinct clusters of universes that survive the math. Alongside the standard model, a small, strange island of alternative universes also survived the cut. In these realities, the strength of dark energy actually decreases over time. Because DES used completely independent data and different observing strategies, it confirmed that DESI's bizarre hint of weakening dark energy was a physical possibility, rather than a mechanical glitch or an analytical bias. At the absolute limit of our knowledge, the hardest part of science isn't making an observation. It's proving to yourself that you haven't been fooled by your own equipment. Over the next decade, observatories like Euclid, the Roman Space Telescope, and the Vera C. Rubin Observatory will come online to ask even tougher physical questions. With every new telescope, we force the remaining hypothetical realities to face new tests. We will keep giving them chances to fail, whittling down infinity until we isolate our exact singular spacetime.